mathematics. Today's speaker is Shimon Corcos. He is a PhD candidate at UKZN. He's done all of his studies at UKZN, completing his honors degree in 2021.
Yes.
And then he proceeded to complete a master's degree under the supervision of Professor Babalal, which he then upgraded to a PhD last year. He plans to submit his PhD thesis at the end of December this year, and we're really looking forward to that. In addition, Shimon is, well, he's racked up quite a few accolades. Some of them include being invited as a young researcher to the Heidelberg Laureate Firm, and so we have quite a few other young people here who've had that opportunity. And most recently, he won first place at a national competition for the 3-minute thesis, as well as last year, I remember he took first place for his 20-minute presentation. So we're really looking forward to your talk.
45 minutes.
This time it's 45 minutes. 45 minutes.
No pressure.
Yeah.
Okay. Thank you, Stuart, for that lovely introduction, and welcome everybody. It is a pleasure to be giving my first seminar. So today I'm speaking about, the title was quite a mouthful, but essentially I'm speaking about 3 aspects: cellularity, sobriety, and preregularity, in a structure that's called lower Vietoris topology. Now, for those of you that are unfamiliar with the subject of topology, which is my research area, I would just like you to keep that word in mind as we go through this talk. So what is topology? Topology is essentially the study of properties of geometric spaces that are preserved under continuous deformations, like stretching, twisting, or bending, but not cutting or gluing. Now, we can study large classes of geometric spaces by abstracting that notion. In topology, we study what is called a topological space. As an example of see, a coffee cup can be deformed into a donut. And from a topological point of view, they can be said to be equivalent. As I said, we work with an abstract notion of a topological space. It consists of a set of points, as well as a family of subsets of those points called a topology. The members of the topology are said to be open subsets of our set of points, which I'm calling here X. And if we are given any family of subsets of X, we can generate some topology on X by taking, to be opened, arbitrary unions of finite intersections of this family S. I'm sure we're all familiar with the sets of real numbers. There's a usual topology that we describe on the real numbers, where we call a set open. While the open sets are generated by the open intervals, where if we given a rational number R, then the set of real numbers that are greater than R is open, and the set of real numbers that are less than R is open. And through the process that we described earlier, we can generate all of the open sets are arbitrary unions of open intervals of the real numbers. Some of you may be familiar with the notion of a metric space, which consists of a set X together with a metric D that is sort of like a distance function. Now, this admits a topology, which is generated by a set we call open balls, where if you take a central point and some positive real number epsilon, you can consider the set of all points in the space which are whose distance from that central point X is strictly less than epsilon. And this generates a topology which fits with that metric, allowing us to study properties of the metric space in an easier manner than with the metric alone. Let's talk about some common notions of subsets of topological spaces. If we're given a subset A of X, we say it's closed if it is the set of points lying outside some open subset of X. And assuming that A is not, well, dropping the assumption that A is closed, we can define the smallest closed set in X containing A, which we call the closure of A. If the closure of A is the whole space X, we say that A is dense X. The interior of A is the largest open set that is contained in A. And A can also become a topological space that inherits many of the properties of X by being given the subspace topology, and we then call A a subspace of X. Now I'm going to discuss two topological properties of spaces. We say that a space is compact if whenever it's covered by a family of open sets, then there is a finite number of them that also cover the space X. And X is discrete if all of the subsets of X are open. Here I'm defining a topological space that we discussed throughout the talk. If we have a family of topological spaces, we call these factors, then we can consider their Cartesian product. And we define the topological product where the points are ordered collections of points, each of which come from each of these factors. And we can generate a topology on it, which is generated by sets of the following form, where if you take a particular factor and an open in that factor, you can consider the set of all points where if that factor is xj, then the jth coordinate must be in that open from xj. If we take n copies, where n is a natural number, of a single space, then and we consider that product, we call that the nth power of x. Now, I'm saying that, which I haven't seen this space called by this name in the literature, but I'm saying that the augmented nth power of x is the subspace of this, where the coordinates of any point are all distinct from each other. Now, here's a notion that is sort of central to this talk, and that is of a hyperspace, which is a special type of topological space that where the points are non-empty subsets of some other space that we call the base space. So here my hyperspace is F, and my base space is X. This set here, P naught of X, denotes the set of all non-empty subsets of X. This notion was introduced since the first definition of a topological space by in 1914, where he investigated metric on the set of closed and bounded subsets of any metric space. And we know that now to be the Hausdorff metric. This is still the most extensively studied structure on hyperspaces in the literature. The second most extensively studied structure is the Vietoris topology, which can be defined when the base space X is any topological space. And this can also be defined on, this can also be defined on any set of subsets of X. In 1951, there was a mathematician, Ernest Michael, who noticed that we can study the Vietoris topology from two quarter topologies, which we call the lower and upper Vietoris topologies. Here today, we are studying the lower Vietoris topology. And before I forget, there is a big book by Alejandro Irreducibility and Sam Nadler Jr., which dedicates to the applications that the Hausdorff metric and the Vietoris topology have to general topology, where they study some exotic topological spaces and hyperspaces and other spaces. So today we are focusing on the lower Vietoris topology, which has applications in category theory, the study of multi-valued functions, and in order theory. In particular, the lower Vietoris topology, if you look at that on the set of all closed sets of space, that's called the Hoare power space. That is a topological representation of what is known as the Hoare power domain or power locale, which models a computer science design principle called angelic non-determinism. So if we are given an arbitrary hyperspace of our base space X, then we say that the lower Vietoris topology on it is the one which is generated by these sets, where if you take a fixed open in X, then we consider the set of elements of the hyperspace which all meet that open V. And the closed sets are generated by, if you take a particular closed set U in X, and you consider the set of elements of the hyperspace which are subsets.
Shimon,
Yes.
that angle bracket V1, Vn, isn't that A contained in the union of the Vi as well? No?
Yes, absolutely.
Yeah.
That's true, yes. And that's why if you consider just a single one of these, say V1, and you close the angle bracket, that's how you get this to be the set of elements of the hyperspace that are subsets. So yes, that's right. Several topological properties have been investigated with low-Vietoris topology, like compactness and the countability axioms. But one property which has not been investigated is the cellularity of space. Now, I need to quickly go over what we mean by cardinals. So we work in a theory of sets called the Zermelo-Fraenkel set theory with choice. In it, we can represent the size of a set by another set, which we call the cardinal of that set. And in this theory, we can compare any two cardinals by an order that looks like this. If we've got two cardinals, kappa and lambda, we say that kappa is less than or equal to lambda if whenever you have a set A with cardinal kappa and B with cardinal lambda, then there is a one-to-one function from A to B. Cardinals can be infinite, and the smallest infinite cardinal, which we call the countably infinite one, is the cardinal of the natural numbers. And in this theory, any family of cardinals has a smallest element. So we can then define the cellularity of a space to be the smallest cardinal where it is greater than or equal to the cardinal of any disjoint family of opens in that space. In other words, the cellularity is the supremum of all cardinals associated with disjoint families of opens in the base space. Many of the papers I've read in the literature assume that the cellularity is infinite, which is a reasonable assumption because if you have an infinite Hausdorff space, that always has infinite cellularity. We say that the space is Hausdorff when distinct points have disjoint open neighborhoods. The only subspaces of a Hausdorff space that have finite cellularity are the finite subspaces. But if you're looking at spaces which are used, say, in algebraic geometry, you can come across the notion of a Noetherian space, where the descending chain condition holds for the closed sets. And in that space, every subspace has finite cellularity. A good question to ask is, if you know what the cellularity of a space is it guaranteed that you can find a family of disjoint opens whose cardinal is that cellularity? Well, if you know that the cellularity of X is either countable, a singular, or a successor cardinal, then indeed you can find a disjoint family of opens in X whose cardinal is the cellularity. Any cardinal has an immediate successor, the one that immediately comes after it. And we say that a cardinal is singular if it is a union of, so say kappa is singular, if it is a union of less than kappa smaller cardinals. However, if you have a weakly inaccessible cardinal, which is not guaranteed to exist in our theory of sets, then you can find a space. So if you have a weakly inaccessible cardinal lambda, and you consider the product of discrete spaces having cardinal kappa less than lambda, then it has cellularity lambda, but no disjoint family of opens of cardinal lambda. Now, something strange happens with the low Vietoris topology. The usual hyperspaces that are studied in the literature all have cellularity 1, which means that every pair of open sets must meet with each other. In particular, we have the sets of all non-empty subsets X being irreducible, which means exactly having cellularity 1. And the closure of the space of finite subsets is the set of all non-empty subsets X. So if the space of finite subsets is a subset of the closure of some hyperspace, then that hyperspace will be irreducible. And then so is the following hyperspaces. The space of closed subsets of X, which is the whole power space I mentioned earlier, space of compact subsets, and space of finite subsets. Irreducibility is useful for studying closure in these hyperspaces. And here I've proven a result that shows that. But what I would like to get to is hyperspaces for which the study of cellularity becomes more interesting. We say that the symmetric end product of X is the space of finite subsets of X having at most n elements of some natural number n. And then we also consider the subspace of finite subsets having exactly n elements. So we can determine exactly when they're irreducible. We can prove that their closures are the same. You can replace U here with the base space X. Their closures are the same. And by a result which I failed to mention earlier, that means that the cellularities are the same. Now, why that's important is because we want to prove a general result about the cellularities of these spaces. It was in 1998 that Vietoris investigated the Vietoris topology, not the lower one, on these hyperspaces when the base space is half-full. And he proved that the cellularity of these spaces is the same as the cellularity of the nth power and the augmented nth power. So this is what we aim to do for the lower Vietoris topology, but without the assumption that X is half. And he proved this by considering certain types of mappings that preserve cellularity in some way. So let me first define a few notions. We say that if a function f from space X to space Y is a mapping, if f is onto and the pre-images of any open set is open. So this is really just an onto continuous function. And it's easy to show that in this case, the cellularity of Y is always at most the cellularity of X. But to have equality here is you don't it's not as simple to get, right? So we need to define a few things first. A mapping is open if it preserves open sets, and it's perfect if it preserves closed sets, but also if the fibers, which are the pre-images of points, are all compact. And if f is one-to-one and open, we say that X and Y are homeomorphic spaces. Open perfect maps are very strong. They're very close to homomorphism. But even then, it is not enough to show that the cellularities of those spaces would be the same. And let me first introduce this notion here. A space is thick enough if it is half-full, and if you have a point lying outside of a closed set, you can separate them by a real-valued mapping. Now, in 1995, Vietoris proved that if you have an uncountable cardinal, you can find Tikhonov spaces X and Y, and an open perfect mapping from X to Y with not just compact, but actually finite fibers. Every finite space is compact, such that Y has countably infinite cellularity, but the cellularity of X is kappa, which is more than that. And the types of map that we need to look for, actually, it doesn't result from strengthening the properties of the maps has, but rather restricting the fibers. And here I need to introduce another notion. Mapping is quasi-open if the interior of the image of any open set is non-empty. So what it means is that the image will contain some open sets. So Vietoris in 1995, he proved that if you've got a quasi-open mapping from X to Y, and there is some natural number that bounds all of the fibers, and you know that the cellularity of X is infinite, then you can show that the cellularity of these spaces is the same. So that's the result that we are going to make use of. When Vietoris proved his results on cellularity in the Vietoris topology, he considered these mappings. So here I hat is the map from the nth power of X to the symmetric end product, which sends in a point of n coordinates to the set containing those points. And we consider as well the restriction of that map to the augmented nth power, where the image is the set of all n element subsets. Both of these are mappings, and the fibers of J hat have exactly n factorial elements each. We won't describe specifically when I hat is quasi-open, because we can easily show that if I hat is quasi-open, then so is J hat. And we want to find conditions under which J hat is quasi-open. First, I want to discuss what has been proved in the literature already regarding these maps. Vietoris proved that if X is Hausdorff and this space has the Vietoris topology, then this J hat map is open. And in 2001, Costantini and colleagues proved that if X is Hausdorff, then J hat is not just open, but it is a covering mapping, which is significantly stronger than being open. And this is when this space of n element sets has the lower Vietoris topology. So we say that if f is a function from x to y, it's a covering mapping. If any point in y has an open neighborhood, if any point in y has our function f from x to y is covering. If any point in y has an open neighborhood whose pre-image is a union of disjoint opens, say B alpha, which are all homeomorphic to you under this map F. Here's an explanation on why this map is covering, but I won't go through that now. So here I describe when I hats and J hat could be open, but not just open, something more general when they are quotients. A mapping f from x to y is quotient if you have an open set in y, if you have a subset of y whose pre-image is open, then that set must be open in y. Every open mapping is quotient. Now, it is a useless endeavor to try and figure out when I hat is open for our purposes, because the only time it is a quotient mapping is when X has the trivial topology. But for J hat, the situation is more hopeful. J hat is quotient if and only if X is Hausdorff, so that generalizes the previous result by Vietoris. Also, it is equivalent to saying that J hat is a perfect covering mapping. And that also generalizes the earlier result by Costantini. In this case, the topology on the n element set is actually the same as the Vietoris topology. And here I describe when J hat is quasi-open exactly. There is a trivial case that we need to sort out, and that is if X has a largest open set which is discrete and has less than n elements, then J hat is quasi-open. So that's not very important. But what is important is that if you assume that such an open does not exist, then J hat is quasi-open if and only if, whenever V is an open set in X, which has more than n elements, then its cellularity must be at least n. Otherwise, V is discrete. But we can unpack this because if I had an open set V with cellularity, say n, it consists of these irreducible components, n of them. And if one of those irreducible components has more than n elements and is open, then it will also satisfy this condition. So that is why I endeavored to prove this third condition, which describes more specifically what happens in the space X. if this is satisfied. Firstly, every finite open is discrete. And secondly, if you've got an infinite open that has finite cellularity, then you can find a dense open discrete subspace, which is finite and has the same number of elements as the cellularity of V. Also, I was able to show that certain things happen with the closure of elements of F, which I'm trying to see how much time I have left here.
You have 90 minutes.
19 minutes. Okay. Oh, 90 minutes. Okay. Well, there we go. Now, maybe I can say here quickly that, so we know that F is dense in V. So if you take a subset G of F, something different happens if it's got less than n elements and if it's got at least n elements. If it's got less than n elements, then actually the elements of G are the only elements in V which is not in the closure of the remaining points of F. It is also the largest open subset of the closure of V, which does not contain any of the other points of F. And then if you knew that G has at least n elements, what you can show is that this open set is a subset of the elements of G together with intersections of closures of elements of G. And that is described by how many more elements G has than simply n minus 1 elements. See? So I wanted to give you an example of exactly where this, or I should rather say, I wanted to give you an example where this condition is satisfied very closely. But to do that, I need to introduce a few notions. We say that X is T1 and all of its points are closed. We say that X is quasi-sober if all of its non-empty, irreducible, and closed subspaces is the closure of some points. It is sober if we specify that these types of spaces must be the closure of some unique points. The sober property is more commonly discussed, but we're introducing quasi-sober because it enables us to have an easier notion to work with when we encounter non-linear spaces. And what's relevant here, why I'm introducing this notion, is because if you've got a quasi-sober space and you have a subspace with cellularity n, then the closure of some n element subset of A. So what that would mean for this result is that if V is infinite open and has finite cellularity, and we know that X is quasi-sober, then we can already find a dense finite subspace. We say that X is T0 if distinct points have distinct closures. And these are listed in order from strongest to weakest property. The example on the next slide that I'm going to show you makes use of a topology called the upper interval topology, which is defined in any partially ordered set. And it's the one where the closed sets are generated by the down sets in that partially ordered set. Where if you've got an element X in X, then the down set is set to all points Y, where Y is less than or equal to X. Now, here, this example, we're fixing a natural number n, and we're letting X be the union of n number of points and a countably infinite set Y, which are disjoint from each other. And we're supposing that every element of Y is less than each of the elements in this finite set. And then we're supposing that X has the upper interval topology, which is induced from this order. What we end up with is that, yes, the finite open sets are all discrete because they are subsets of F. F is discrete because none of the points are in the closures of any of the other points. Any infinite open set B is actually density X, which is the closure of this finite set F. So any infinite open set has cellularity N here. And then we proved these equalities, which mimic what has happened in this theorem. Also, this space is not a sober space. It is T0, but it's not T1. And so because the space X satisfies the properties in our theorem, our map J hat is quasi-open. However, we should note that we can actually show that this hyperspace of n element sets is irreducible, so it's got cellularity 1, but the nth power has cellularity n to the n, and this, in this example, it will be the same as the cellularity of the augmented nth power. So you see, using the result from Vietoris that I mentioned earlier, and our result that we proved, we would have the cellularity of these spaces being the same, but here it's not the same. And that's why it's important to assume the cellularity of X being infinite. So this is what I was talking about just now, that from our theorem, we know that if cellularity of X is infinite and J hat is quasi-open, then the cellularity of the symmetric n product and the hyperspace of n element sets is the cellularity of the augmented nth power. We're not finished yet because we still need to show that this is the cellularity of the nth power. So what do we know already? Well, because we had a mapping earlier, I had, from the nth power to the symmetric n product, we know that the cellularity of the symmetric n product is less than or equal to the cellularity of the nth power. And so the cellularity of the augmented nth power is at most the cellularity of the space. So the question is, when is it true that we have these spaces having the same cellularity? And we can actually show that for any space with infinite cellularity. What was shown previously is that by, again, Vietoris, is that if X is Hausdorff, then this augmented nth power is open in the nth power, and some other condition is satisfied. Now, in general, this augmented nth power is not open in the nth power. In fact, it's only true when X is Hausdorff, so we couldn't use that result. And we couldn't use, remember I said that the cellularity of a space is the same as its closure. So we tried to see if we could get the closure of the augmented nth power to be the nth power, but that's not true in general. What we were able to show through we had to sort through quite a few finicky details to get that actually, whenever the cellularity of X is infinite, then indeed we do have the cellularity of the nth power being at most the cellularity of the augmented nth power. And this is not just when our map J hat is open, but this is true in general. And so we have our theorem, which says that if you have a space where every finite open is discrete and every infinite open has a deep cellularity n, and you know that the cellularity of X is infinite, then the cellularity of all these spaces is the same. It is also greater than or equal to the cellularity of X. Determining cellularity in products is not simple. But we can look in various textbooks on cardinal functions, like say, True-Hatcher's book on cardinal functions, to say that if the cellularity of x is infinite, then the cellularity of the nth power is the supremum of the cellularities of powers less than that. So we know from that the cellularity of the nth power is greater than or equal to the cellularity of x. So one question that you may ask is this, does this inequality ever become strict? Yes. In our version of set theory, yes, it does. A well-known set theorist, Stebor Todorchevich, he proved that if you've got a cardinal, well, if you look at the exponential of the count of the infinite cardinal, this means the cardinal of the power sets of the natural numbers. Consider its successor, and consider repeated successions, accounts of the infinite number of repeated successions, and take their union. We're calling this union cover. Then for every natural number bigger than or equal to 1, you can find a compact Hausdorff space where the cellularity of x is the same as its nth power and is also kappa, but the cellularity of the n plus 1 power is greater than kappa. So what this means for our results is that the cellularity of the hyperspace of n plus 1 element sets would be greater than kappa, which would be the cellularity of our base space. And we actually do have equality in some cases. If you know that x has a countable dense subset, then what you can show is that the cellularity of all of these is the countably infinite cardinal. If you assume a particular axiom of set theory called Martin's axiom, then if you know that the cellularity of x is countable, then the cellularity of the nth power is also countable, and so you have equality as well. So the example that I mentioned earlier where J hat is quasi-open, that had finite cellularity. Here is an example where J hat is quasi-open, X is not Hausdorff, and has infinite cellularity. And in this example, well, this example is a well-known one of a sober T1 space which is not Hausdorff. Consider the set of real numbers with an added point P, where the open sets are the opens in R, as well as cofinite subsets of R together with that P. Then indeed you can show that X is not Hausdorff, it is T1 and sober, and the set of rationals together with this point P is dense in X. And you can show that this means that X is countably infinite cellularity. And so that really concludes our discussion on cellularity in the lower Vietoris topology. It has been a pleasure talking with you about this. Thank you for listening.
Questions or comments? Question 1.
When working with product spaces, the results usually rely on the axiom of choice quite heavily. Where did you use the axiom of choice for your result?
Well, that's the thing, is that because I'm working in that theory so much, is that I don't really pay attention to where I use the axiom specifically. But and even in Juhash's book, where he states those results on cellularity in powers and products, I don't see where he mentions the acting choice.
So you don't see it in the proofs, but maybe you are using a result that rely on it.
Inherently, yes. I mean, the cellularity of the empty set would be noughts. You know, so yes. Yes, I'm sure the axiom choice is inherently used in those results.
Go ahead. I have a very weird question. It may be complete nonsense, but in chess, okay, it's not like it's well known that you can place 8 queens on the chessboard so that none of them is eating any other queens, but you cannot place 9 queens.
You mean that none of the queens are on the same row and column as each other? Is that what you mean?
Also in the diagonal, everything. So they're really, in the next move, none of them can eat any of the other ones. So my question is, as you can only place 8, but never 9, do you think this can have anything to do with cellularity?
I'm not sure. One thing I will say, we've read Robert Floyd's paper on non-deterministic algorithms.
No.
That mentions the 8 queens problem.
Okay.
With regards, so he uses, or he models a solution of that problem using non-determinism.
Okay.
Yeah, that's completely unrelated.
Yeah, I check. It's just that maybe they are, I don't know, disjoint opens side, but you cannot place one more. I don't know.
I don't know, can a chess board be represented as a topological space?
I don't know.
Yeah, mine is not so much a question, more a comment. You know, we come from the background of gravity, simple people. Points to talk about gravity. So I get really excited to mention when you use the ultra measure. But if I understand you correctly, you're really thinking of a metric or pseudo-domain manifold points. And what you call the house of metric is something, the distance in effect is not some point. So, am I right that that can't really be applied to a gravitational context?
Well, it depends, because, I mean, I haven't read it myself. I mean, not in depth. But there's a book that's dedicated to the study of the Hausdorff metric to other topological spaces, where they actually model certain topological spaces as hyperspaces with the Hausdorff metric, which enables them to prove things about those spaces which couldn't otherwise prove, not using topology. So maybe one of those spaces is used in gravity. Not sure. Yeah.
Well, then there are no further questions.
Okay. Just one last one. This notion of a power domain in computer science, I mean, it's closely related to hyperspaces, right? Because they're considering certain collections of a particular domain, I would think, where a domain is a continuous pose set, which is also a DCPL. Is that correct? Is that correct? Yeah.
From you know more than that. When you're looking at the power locale, or the yes, power locale, then you are looking at a frame that's really generated by generating elements, where the generating elements come from some other locale. So maybe the power domain is defined similarly.
while we got this question, something came through from Narcisse online.
Okay.
And the question is, you mentioned the lower regions.
Is there an upper?
Yes.
Yes, there is an upper. We go back. Yeah, see the lower and upper Vietoris topologies together, they form a foundation for the Vietoris topology. Yes, so there is a notion of lower and upper.
So I hope we've answered that question for you, Narcisse. Apart from that, everybody else who's watching online doesn't have any further questions. They basically said thank you in the comments. And if there's no further questions here, then let's thank Shimon one last time.